This is Lesson 1 of Unit 8, Applications of Integration. And this lesson focuses on finding the average value for integrals. So the first topic is talking about the average value of a function on an interval. So we know that the area of a region under curve is greater than the actual area when we do a inscribed rectangle, and less when we use circumscribed rectangle when we're finding area. So the mean value theorem for integrals, and this is a new theorem for us here, the mean value theorem for integrals states that somewhere in between the inscribed and circumscribed rectangles, there's a perfect rectangle whose area is precisely equal to the area of the region under the curve. So let's take a look at this picture here and break this down a little bit more. So if f is continuous on the closed interval a to b, then there exists some number c in the closed interval a to b such that the integral from a to b of f of x dx is equal to f of c times b minus a. So what they're showing is that green rectangle there will give the perfect area of the area under the curve. Now there is a note here, and that note is kind of important. It says that, again, the mean value theorem doesn't tell you how to find c, just says it exists. So this is another one of our existence theorem. So what we want to remember is that the average value of the function, the value of f of c given in the mean value theorem for integrals, is called the average value of f on the interval. So you may be asked to do that. Find the average value of the function over an interval. So how do we go about doing that? So we want to make sure that we know that f is integrable on the closed interval. Then the average, or the mean value, they might ask you for the mean area, is given by 1 over b minus a times the integral of a to b times f of x dx. You can also write the theorem this way, where you put the b minus a on the bottom, and what you're doing is you're taking the area divided by the width of the interval. And this is equal to, and we want to make sure we understand that there's going to be an f of c that we're looking for, and that's the average height. So let's go through and do a couple of examples here with this. So example 1 says, given f of x is equal to 3x squared minus 2x, find the average area of f on the interval from 1 to 4. So just pointing out some things here. We want to know that a is our 1 and b is our 4. So we are looking to use this little formula. We just have 1 over b minus a times the integral from a to b of f of x dx. And so we're going to substitute everything in. So we have 1 over 4 minus 1 times the integral from 1 to 4 of 3x squared minus 2x dx. And now it's just a matter of doing the mechanics of this. So we have 1/3 times x to the third minus x squared. Whoops, I don't know why I wrote a 2 there. Minus x squared. And we're evaluating this from 1 to 4. So we get 1/3 times, and our first substituting our upper bound, we get 64 minus 16 minus 1 minus 1. So we get 0 for that one. Okay, simplifying, we get 1/3 times 48, which is 16. So that is our answer, 16. Okay, part B. So now we want to find that value of c, guaranteed by the mean value theorem for integrals. So here's what we know, is that we know the integral from 1 to 4 of 3x squared minus 2x dx has to be equal to our f of c times our interval. So we can use that to help us find f of c. So solving this, we know already that the value of our integral is 48. So we're going to have 48 equals 3 times f of c. So f of c is going to equal 16. So now we can use that to find our C. So how we use this is we're now going to set that equal to our function. So we're going to I'm going to use C as the variable. So f of C is really, here's my f, is going to be 3c squared minus 2c equals 16. And so now I'm going to solve that. So I have 3c squared minus 2c minus 16 equals 0. And this factors into 3c minus 8 times c plus 2. And we can ignore this one because our interval is from 1 to 4, so a negative number will not be on our closed interval. So our C is going to be 8/3. Okay, question 2, which we can now use a calculator for. In 2000, the world's population was 6.1 billion people, and the relative rate of growth was 1.4% per year. This can be modeled by the function n of t equals 6.1 times e to the 0.014t, where n is the people in billions and t is the number of years since 2000. Assuming this model remains true until 2050, find the average population of the world between the years 2010 and 2020. What are the units? So we want, if you notice, it says right there, the average population. So we're going to use our mean value theorem for integrals. So we're looking between 2010 and 2020, and our baseline time is 2000. So our integral boundaries are going to be 10 and 20. So we're going to have 1 over 20 minus 10 times the integral from 10 to 20 of 6.1 times e to the 0.014t dt. And so this is going to be 1/10 times this integral. And the nice thing is, since I can use my calculator, I am just going to put that in my calculator, crunch the buttons using the integral feature, save me time and energy. So this is approximately equal to 7.532. Now, if you don't remember how to put an integral in your calculator, please ask in class. It's a couple of buttons, whether you have an Inspire or an 84, and it saves you a ton of time. So we want to write a statement since it's asking us what the units are. So what we can say is that the average population of the world between 2010 and 2020 is approximately 7.532 billion people. All right, now example 3 again is another calculator one. Suppose C of t represents the daily cost for air conditioning in your house in dollars per day. So what you want to notice here is that this is a rate, where t is the time in days and 0 represents and t equals 0 corresponds to July 1st, 2017. Explain what the following expressions represent in real world terms, including the units. Okay, so the first one, if you notice, we are just finding the displacement here, the area under the curve from 0 to 90 of C of t. So this is going to be the total cost for air conditioning and we want to figure out how far 90 days is. So it's from July 1st to September 28th, of 2017. Okay, and the next one, the only difference between A and B is the introduction of that fraction. So that changes it from the total cost to the average cost. For our air conditioning in the same time frame. And this is in dollars per day. You could have listed all the dates again. I'm just showing you another way to write the date range if you didn't want to figure out from July 1st to September 28th. So you could say for 90 days starting at July 1st. That would work as well. Okay, so we're going to end this video with an American hero, Mr. Chuck Yeager. On October 14th, 1947, Charles Chuck Yeager flew his X-1 rocket plane at an altitude of 12.8 kilometers. He was clocked at 299.5 meters per second, which is about 670 miles per hour. So if you can imagine how fast that was. At different altitudes, sound travels at different speeds. We can model this variation for speed of sound with a piecewise defined function given below. And the data for this was found at this website. And in case you don't know this, that is when Chuck Yeager broke the sound barrier, and everybody was amazed. They didn't expect that a noise would be made when you went faster than the speed of sound. And many people thought he had died or the jet had exploded or something. So it's a very interesting story. So we are asked to integrate the function s of t over the interval from 0 to 80 for the 5 subintervals, and that's seconds. And then we are to apply the mean value theorem for integrals to find the average speed of sound over different altitudes. And finally, we're going to draw that average value s of c on the graph. So you can see we've divided this area up into 5 parts. So we're going to have to integrate each part separately since it's a piecewise function. And then we will, for part B, add those together and divide them by our time interval, which is going to be 80 seconds. So for part A, we have a lot of number crunching to do here. So for part A, I'm just going to number these 1, 2, 3, 4, and 5. Okay, so for 1, what we're going to do is we're going to do the integral from 0 to 11.5 of negative 4t plus 341 dt. And when we do that, we get negative 2t squared plus 341 t, and that's going to be evaluated between 0 and 11.5. And it doesn't say this, but this is definitely one you'd be using your calculator for. So you get, when you do this, you get 3,657. And then we're going to do 2. And then we're going to do the integral from 11.5 to 22 of 295 dt. So that's just going to be 295 times 22 minus 11.5. So when we do that, we get 3,097.5. And then I'm going to start alternating colors here so it's easier to follow. So for section 3, we're going to do the integral from 22 to, what's our upper limit? 32 of 0.75 t plus 278.5 dt. And so we get 0.375 t squared plus 278.5 t, and that's going to be evaluated between 22 and 32. And when we do that, we get 2,900 87.5. Okay, and two more. So 4, we're going to do from 32 to 50 of 1.5 t plus 254.5 dt. And when we integrate that, we get 0.75 t squared plus 254.5 t integrated from 32 to 50. And when we substitute those values in, we get 5,688. And through the magic of electronics, I can extend off the page. And I'm going to need another color here. I use light blue. And for number 5, I'm going to do the integral from 50 to 80 of negative 1.5 t plus 404.5 dt. And so I'll be integrating negative, and when I integrate, I should say, negative 0.75 t squared plus 404.5 t evaluated between 50 and 80. And that gives me a value of 9,210. So that is the answer to part A. Let me just zoom in a little bit here so you can see the whole thing. So you can see all those values. And then what we're going to do for part B is we're going to find the average value. So we have the value for each one. So for part B, what we're going to do is we're going to take 1 over 80 minus 0 and integrate from 0 to 80, the entire length of our time. And so that's just a matter of adding all these values together for each section. And then we're going to divide it by our 80. And this all gets divided by that 80 minus 0. And so when we do that, we get 308 meters per second. So not being really savvy on going back and forth about how fast that is, in case you're wondering, it does come out to be approximately, it's a little less than 689 miles per hour. So that was moving pretty fast. So the last thing we're asked to do then is, part C says, to draw the average value on the graph. So what you want to do is you want to take a ruler, find 308, because the graph is in meters per second, on the Y, and we're just going to draw a horizontal line across the graph right here. That's a little low. Let me move that up a little bit. So right along there. So there's my 308 meters per second. Okay, so this now ends our introduction into applications of integration.